I want to quote here Benjamin Disraeli. One secret of success in life is to be ready for his or her opportunity when it comes. Here is a man who never misses an opportunity for a design of a precast building. I am very happy for working along with him for an indoor stadium at Bapatla in Andhra Pradesh. He is none other than Sanjeev Sharma, Director, Lior Structural Solutions. Sanjeev Sharma is a structural engineer with 25 years of international experience in structural analysis and design of precast buildings and structures, and it is Director of Lior Structural Solutions, a company offering structural consultancy services for precast and conventional buildings and structures. He has participated in structural design and detailing of more than 500 small and large-scale projects worldwide using modern construction technologies such as precast and prestressed concrete. He holds master's degree in structural engineering from US and has worked in Dubai for 10 years before founding Lior Structural Solutions in India in 2012. Lior Structural Solutions offers precast structural engineering services in India and outside India for buildings that include residential, hotel, IT, commercial, retail, health, institutional, industrial, stadium buildings, including tall building structures. The services include concept design to production level detailing using advanced softwares for analysis, design, and 3D building information modeling. I request Mr. Sharma to come over to the dais and deliver his address.
Good morning to all. Thank you, PSI, for giving me an opportunity to present precast system and connections, including case study of build structure, to a wonderful audience. Precast concrete consists of concrete that is cast into a specific shape at a location other than its final service location. So the concrete is placed in a form, as you can see on the right side image, typically a steel, and cured before being stripped from the form. These components are then transported to the construction site, erected into place and connected to make a structure. Precast concrete can be plant cast or site cast. So what are the benefits of precast construction? I think most of us would have already noticed that speed, all-weather construction, reduced labor, reduced activities and materials, automated process, better quality control, architecturally pleasing, reduced wastage, and in short, it is industrialization of construction industry. So, type of buildings that can be made in precast: residential buildings, as you can see, these are all real structures done in precast, commercial offices, hotels, institutional buildings, schools, museums. This is Mughal Museum near Agra, stadiums, car parks, multi-level car parks, retail buildings such as malls, even religious buildings. This is a Hindu temple in Omaha, USA, which I got an opportunity to visit in 2020. It's done in precast with double T slabs. In healthcare industry, hospitals, industrial buildings, the Bapatla, which Mr. Reddy was talking about, airports, where large spans are required, bridges. Of course, most of the bridges in India are now being built in precast construction, silos, watchtowers, chimneys, boundary walls, cladding, facade, you name it, and precast can deliver you that solution. So even other infrastructure products such as piles, roads, pavements, tunnels, culverts, drains, pipes, retaining walls, noise barriers, etc. So what do we need for precast? First of all, we need a plant. So a plant can be a very simple outdoor plant at site for small scale precast projects, or it can be a state-of-the-art factory, with long line pre-stressing beds or tables, either stationary or circulatory carousel systems. And I think most of us have become familiar with this factory. So you need a plant and a storage space, as you can see it, and your batching plant and other accessories. So I will be talking more about the structural system, how a building can be envisaged in precast. So to come to a structural system, we need to know what are the elements that can be, made in precast. So what are the elements of a building? We have slabs, we have beams, we have walls, we have columns, staircase, even foundations. So all these individual elements can be made in precast and then assembled in different ways to get different structural systems. So we define the structural systems by the way they carry the load or resist the load, you would say. The vertical loads, the gravity loads, and the lateral loads, such as wind and seismic. So this shows basically an arrangement of slabs. So we don't have a pointer, but as you can see here, we have labeled A to G, and the elements are there. So we'll talk about slabs. We can make solid slabs in precast. Thank you. We can make solid slabs in precast, hollow core slabs, double T slabs, as you can see here, with or without topping. Slabs with lattice girder, some people call them filigree slabs, solid slabs, and ribbed slabs. So each of the ribbed slabs can be downwards or upwards as required. So depending upon the span available in a building, we can choose which type of slab works best. So for smaller spans, there is no point going with pre-stressing because that helps only when you have a longer, larger spans. So for smaller spans, you can have up to 5 meter. A solid slab works very well. Typically for residential buildings where the room sizes are limited to less than 5 meter, we can go with the solid slabs. Hollow core slabs for longer span though, nowadays we also get 100 and 120 mm slabs which can start giving you solutions from 3 meter onwards. So if you have a plant already with hollow core, yes, you can replace solid slabs with smaller, thinner hollow core slabs as well. Double T slabs for longer spans like 10 to 20 meter, hollow core is good for 4 to 15 meter. Ribbed slabs, again, because they are not pre-stressed, 5 to 10 meter, and double T slabs, they are pre-stressed, they can go really up to 20 meter. So this cross section of double T is the most economical section which consumes the least amount of concrete for a given load or size. Only thing is that it's not as fast in production as hollow core slab, so there are pros and cons. The slabs, they rest on beams. So beams can also be made precast, and there are different types of beams. You can have a rectangular beam. On the rectangular beam, you can have the slab sitting on top of it, so you don't have any ledges. You can have a beam with ledges where you need a space to make the slab sit on it. So if you can see the pointer, this is a ledge. Ledge can be on both the sides, or for very long spans, you can use I-beams. You must have seen in the PSP precast factory, this I-beam was on display, 24 meter, and it can be fairly economical because we remove the concrete from the areas where we don't need it. We don't need concrete in the middle. We need concrete in the top for the compression, and we need concrete in the bottom to hold the strands which take the tension. So we don't need any concrete ideally in the in-between, it's just the shear. So we can remove the concrete from the middle area and make it an I shape, which gives you economy. And you can go large spans with less amount of concrete. Also, beams can be deep or wide because normally in buildings, people don't like to see depths, right? So everybody wants a very shallow floor system. So precast band beams are very ideal because of pre-stressing. You can make thinner slabs, go larger spans. This span is 11.5 meters. So I don't think any cast in situ beam can give you 11 meter with hardly 500 or 600 composite depth. This part is below the in situ part. So we make it partially precast, and the top is left in situ so that my top reinforcement can go over the columns and get integrated well and give you a moment connection over there. These are also the beams, and this is the same beams which we talked about, how it can be seated on it. So we talked about slabs. Slabs sit on the beams rest on the columns or walls. So columns we can do precast easily, any shapes. You can have even Y shape, circular shape, rectangular shape with chamfers, octagonal shape. The beauty is that in one mold, you can cast multiple times, unlike cast in situ where you have to remove the formwork and make it again. So any complicated shape, it's difficult to do in conventional concrete, but in precast, because it's the one mold in which you are going to repeat again and again, you can, give the choice to the client of, or to the architect, any shape. So you can have multi-level columns or each floor height columns depending upon your design requirement. Similarly, walls, we can have walls, load-bearing walls, sandwich walls or solid walls, non-load-bearing facade walls with, pre-finished walls with exposed aggregate, colored concrete, form liner or graphic concrete also, where you can imprint any image. This is basically a project Indira Canteen done by Katera, and in which the photograph of late Mrs. Indira Gandhi was, printed on the concrete itself. Yeah. So from slab to beams to columns and walls, then we need the foundation. Even foundations can be done in precast. We're not talking about the raft foundation, but the isolated or the strip footings can be easily done in precast. So you can have a tapered footing or a straight footing with a pocket for the column to take the moment, or you can have a dowel tube connection as shown here, or you can also use the grouted couplers, chemical couplers. So the dowel tube is an alternative for lap reinforcement, and this coupler is an alternative for a mechanical coupler. So split footings, rectangular footings, and also we have done, interestingly, in some industrial buildings, footings with stiffener, like you do in steel. At the base plate you have a stiffener. So similarly, when footings becomes very large, they tend to require very, unnecessarily, they need very large depths for shear or primarily for shear. So we can always add stiffeners, because this is one mold, as I said, you can make any complicated shape. So you can stiffen the building and go with very narrow strip of, let's say 150 to 200 base, and then add stiffeners to counter the shear or the moments, and that will reduce the amount of concrete. But again, you can go 5 by 5, 5 by 6 meter, especially for industrial buildings. This type of footings can be economical. So we talked about all the structural elements in a building. So other than buildings also, there are many other miscellaneous structural components that can be done in precast. Boundary walls, beautiful boundary walls with patterns on it, stadium bleachers, raker beams, stairs and landings, long span roof beams. This is a 55-meter beam, which is 160 feet plus. So done with I-beam and with hollow web. And it was done in two pieces. It's in Sharjah. It's for a coal factory in Sharjah, and so it was post-tensioned at site and attached. So those were the structural components. Even architecturally, the architectural facade, there's a big industry in Europe and North America which use precast for the architectural facade. So there are precast contractors doing only architectural works and they give you beautiful designs like exposed aggregate, form liner finishes, or you can also have any grooves, any patterns done in the mold. You can just have some steel plates welded in these shapes and get a beautiful pattern out of it, the grooves and recesses. And you can combine the architectural panel with the structural panel, so you do away with so you are merging the functionality of the building with the structural requirement, so you don't have to do double work, like make a structural system and then clad it with an architectural block work or framework. So I wanted to explain the individual elements so that combining those elements, now we can develop the structural system for the building, because there are different structural systems which can be done for the building. So the most common is for low-rise buildings. We have been very familiar with the beam column frame system, which up to 10-12 story works very well, and you don't need any walls in it. So it consists of beams and columns of different shapes and sizes combined to form the skeleton of the building, as you can see here. So there's a beam and column, and the moment connection gives you the strength and stability to resist the lateral loads, whereas the column and beams, they take the gravity loads. So then you have a interior shear wall system where you have still a frame system, but frame is usually not as strong as a wall in the lateral direction, because wall is very long, it can take huge amount of lateral load compared to a beam column frame. So you add normally in the buildings, architecturally we always have lifts areas, core areas. So we use the same walls and make them structural, so that gives the strength to the building, and you still have some nominal strength from the frame structure, and also for the gravity loading you already have the column and beam system. So with this you can do quite a lot of buildings, you know, with up to high rise, 30, 40 story. Another system is like the exterior shear wall system. So some types of buildings, let's say an institutional building, they would like, or a mall building, they would like to have more open spaces inside and won't allow you to put walls inside. So in that case, but architecturally anyway building has to be covered, and not everybody likes glass, right? So some people like to see some, you know, some opaque systems with nice patterns and all. So in that type of architectural arrangement, we can have the outer walls as a structural lateral load resistance system, and inner we can use for gravity the column beams. So we have done Ramiz Mall in Oman with this type of system. So these are the photographs for that. Then a bearing wall system. So even in cast in situ, we all know aluminum formwork system, or we know a tunnel formwork system. So this is exact replica in precast for the same structural system, the same structural performance with the bearing wall system. So in this, we just put slabs and walls. So where is it ideal? It is ideal where architecturally you already have a lot of walls as a functional requirement. So idea is to take that functional requirement, convert it into a structural system, so you don't have to do a double work, right? Most of the residential buildings, you already have plenty of rooms, you need walls as partitions, and if you are able to make that walls into structural walls, that gives you, you know, additional, much additional strength. Though for super tall buildings, that may be a concern of extra stiffness and all, but then that can be merged with the frame system to give you a dual system performances. Also very simple box cell systems. It's something like a volumetric system or a 3D precast system that we saw the presentation yesterday. So we can make the complete room or a house, small house, or an office, site office, prison cells. These type of structures, you know, can be done in a box form, and these are like without any joints at site. So everything is done in the factory. And hybrid precast gels very well with other technologies such as steel or cast in situ. So hybrid construction is also possible, where you have one vertical system in steel or in situ and only the floor system in precast, or vice versa. You can have vertical elements in precast and then you can have the floor in cast in situ or steel, whichever way, you know, the project specifications, you know, work. For the industrial buildings, very good solution in precast because two reasons. One, concrete is very good in fire rating. You don't need any extra coating on it. You just increase the cover and you get the fire performance. For steel sheds, you have to fire paint it or fire coat it. So that's an additional expense. And with pre-stressing, we can go long spans and match the steel structures and even with lesser depths. So like for example, with 1 meter, we can go up to 24 meter. With 1.2 meter, you can go up to 30 meter. And I-beams, so you can have tapered I-beams or rectangular I-beams. These sheds are done in Iraq, and some of them are also being done in India. 2-3 sheds we are doing. Also PSP Precast is doing a couple of sheds in precast using this type of systems. So we studied the precast individual elements, then how to combine those elements to give you a structural system that will work for different types of loadings, for different types of buildings. But the most essential, as somebody yesterday said in one of the presentation, the soul of the precast is the connection. So yes, it's very important to do the connections because they will govern how your building is finally, you know, eventually going to behave. So these are typically the connection locations: a beam sitting on a slab sitting on a beam sitting on a column, column sitting on the foundation. So these are the few areas. In place of column, there can be a wall also. So these are just the few junction areas, and there are several ways to connect the building depending upon what, as a structural engineer, what are you looking from, what performance you are looking for from that type of connection. Is it simply supported? Is it moment resistance? Do you want stiff, non-stiff? So depending on that, you can play with the connections. So broadly, the connections are divided codal-wise into two categories. One is emulative system, which means you connect the building in such a way that the final performance of the building will be same as if it was done in cast in situ. So you are copying the cast in situ system or the behavior, making it precast, but all the joints, everything are complying with provisions that make it act like a cast in situ building. Jointed systems, they have a limited ductility, limited performance at the joints. So the members are much stronger than the joints, but the joints are detailed for performance. And initially they were thought as not very good system. So mostly people are comfortable with emulative systems, but there was a research between Japan and US for almost 10 years, starting 1990s to mid 2000. And they came up with the press connections with the jointed system, which finally said that if designed properly, they can be even better than cast in situ, and they can be very low seismic damage buildings can be done with jointed systems. The design, detailing, the execution is little bit difficult, but I think as we go into the future, yesterday Mr. Ajit Bhate showed one of the system tested that was part of the jointed system. There was some sort of modifications in that, but that falls into the category of a jointed system. So we talk about slab to beam topped connection. So these are, the slides they speak, they convey a lot. So I will not go into much details because time is short and I have to show you some case studies also. Slab to wall connection, slab to slab connection. Integrity is very important. So connections not only is just to rest the structure, but also to make it integral, so that any local failure for some reason should not make the collapse progressive. So they should curb the collapse local only in case there is any accidental failure. So in case of any blast happening somewhere, so this is how we can tie the structure. So there are details available in codes for all these things. Beam to column joints, again I talked about hinge joint or a movement joint, depends upon what type of structure you are looking for. So if it's a small building and you have some shear walls, you can very well go with the hinge joint, pin joint. It's very simple in precast. But if in case you don't have walls, you are depending upon stability on the frame, then you have to make a monolithic column beam junction. So these are the beam and column junctions. We also get a lot of proprietary connections nowadays, like hidden connections, not in India, but yeah, you get in Europe and all. There are suppliers who will give you proprietary connections. They are rated load wise. They will tell you these are rated for such and such load, so the designer can just pick the from the catalog and give those connections here. But in India, mostly we are using still, as I said, that monolithic connections are preferred because of the emulative detailing. Again, column to column connections, we can use dowel tubes, or we can use grouted couplers. So dowel tubes they work like a lapped reinforcement. In place of lap, you can lap it with a dowel tube, and in the coupler, it's exactly a replacement of a mechanical coupler, where the force transfer is directly from the rebar to rebar inside that grouted coupler. So Dextra, NMB, and few others, they are the proprietary suppliers for this. Wall to wall joints are very critical, because if I have a shear wall, so there are going to be forces in the vertical joints and in the horizontal joints whenever any lateral movement is there. And yesterday in one of the presentations, Mr. Gopalakrishnan, he was very skeptical about how these joints are going to behave, vertical joints. But in precast, when we are not sure about the full strength of the joint, you can model it as a gap and still make a very safe design. So this vertical joint, you can model it as a gap and provide a link and design that link only for the force rather than integrating this wall. You will get some reduction in the strength of the wall, but then if you have a building such as residential building with 50-60 walls in a floor, so you have over strength, and that may also help in reducing stiffness, because as some of the staff from our faculty they are worried that some buildings may be extra stiff. We don't need that stiffness. So this is one way of even reducing the stiffness by having, utilizing the precast joints and give some ductility over there. Wall-to-wall horizontal joint. The horizontal joint is a double tube connection, or these are just the images, the connection as I explained earlier. Then column to foundation, again we can have either a bolted connection, a pocket footing, dowel tube, or a grouted coupler. So these are the jointed connections with limited ductility. We use it typically for very, very low-rise buildings, 1 story, 2 story, where you don't have much concern about emulative detailing. And there are advanced precast connections such as wire loops and some proprietary connections like with delta beam, and this is a pico corbel which is a corbel in steel. So you get these connections ready-made from the vendors. They have tested it over years. So they are in the market since 20-25 years. So you just take that, buy that connection for whatever force it is, and you use use these connections. So for all junctions they have a column shoe, wall shoe, and they have a pico corbel, and they also have some wire loops. So these can be bought from the proprietary suppliers. Advanced connections also have very high these are press connections which are highly ductile. They give very low seismic damage. So you can have a column beam system. So yesterday we saw something similar to it that was tested with the company, Mr. Ajit Bhatta's company in Japan. So they had a corbel introduced here, but if you don't have a corbel, this type of system is already researched for 5-10 years and documented in ACI code, and it's known as press connection. This is there is a true joint with the very nice grout over there, and since all the movement is in that joint, your components, beam and column, they remain crack free. So you don't have to repair them during the earthquake or after the earthquake. And similarly in walls, you can have a U-clamp connectors which will take the excess force, get damaged, save the wall, so you can replace these connectors after the earthquake. So these were tests done on these press connections, and as you can see, the same level of drift, 3.5%, cast in situ connection cracks like this, because for the steel to yield, concrete has to crack, otherwise how will the steel yield, right? So when the concrete cracks and earthquake happens of that drift, then you have to come back and repair in all these buildings. So that's why we call it as a damage-free buildings, because the components remain intact, only the joint is affected, and if the grout is very high strength, again that can be, resist much higher loads before any damage is noticed. And similarly, this is rocking type of movement and very less damage. So these are the structures built with this type of systems. The most prominent one is a 39-story Paramount Tower in Los Angeles, California. It's a high seismic zone built with the press connection system and still standing tall. So we come to the case studies. So it's a 4-basement plus 25-story precast commercial building in Hyderabad. So this is 200 meter. It's a huge 100,000 square feet floor plate. And we have a structural system. It got award from the Indian Concrete Institute as Outstanding Concrete Structure 2022, and also it got a Best Pre-Engineered Building Award from Construction Industry Development Council. So this is 25-story tall, 105 meter. It is the tallest currently operational building, precast building in Hyderabad. The primary structural members were hollow core slabs with topping, precast beams, and later loads from wind and earthquake are resisted by a combination of frame and shear walls. So these areas are the core wall areas. This is the back side, front is all open. This is the interior view of it. As you can see, 11 meter, 11.5 meter clear spans with the hollow core slabs. This is another interior view. Offices, that's the front. So we have 3 bays basically in it, 11.5 meter 3 bays. This is the side section view of it, as you can see it. So this is the core area, and that is the column beam area. So the structural system is, as you can see, this is a 250 thick hollow core. Then we have the pre-stressed main beam, 600 deeps here, 1100 wide. So they are coming only 250 to 300 only below the ceiling. The rest is going parallel to the hollow core, so you don't see that depth here. Secondary beams for frame action, 1200 by 485. Precast columns that varied with height, starting from 1400, 1500 size to 1 meter on the upper levels. And we have 11 meter roughly. Yeah, it's pre-stressed, so we were able to manage with 600 depth. Otherwise, in constant situ, you cannot manage. You would need 800, 850 or more, right? Beam to column connections here, we will just show these connections and hollow core sitting on the beams. So this is, if you remember the initial slide, I showed you that the interior shear wall system. So it's something like that. It comes from the interior, then goes, it touches the little bit of the exterior, but primarily it's in the inside, and all the perimeter is frame system. So we have this hollow core system nicely connected with the U-bars and the composite action with the topping. That's how the beam sits on how the slab sits on the beam, and the top 150 mm is without the, it's not precast, so that your top reinforcement can be placed at site and can go over the columns to get you. The bottom bars are projected into the column as well to take the stress reversals, if any. Though with shear wall buildings, you won't notice that much of stress reversals as you get in a framed structure, but still some continuity, good amount of continuity is provided. Similarly, this is how the slab sits on the wall-to-wall connections. This is how 4 beams are coming. As you can see, all the bottom reinforcement is coming and the top reinforcement will also go. So once this is cast, you cannot differentiate it from a cast in situ building because it's fully integrated with the stitch connection. Again, this is column to column connection. So this is a cut section. This is the grouted coupler here, as you can see here. So this rebar goes into this upper column grouted coupler and gives the direct force transfer from rebar to rebar. Similarly, wall-to-wall connections, the same way it happens with the grouted coupler. These connections, when we have this type of connections, we model it as a joint in the wall. This is wire loop connection, and we can, if you want full strength of the wall, you make it stitch connection, rebar coming out, and then stitched at site this part. So that gives you a full strength of the wall. So that was one case study. This is, I will not go into detail of this building because I think time is almost over. So this building is a residential building because many of the viewers here would be interested in knowing the residential buildings also. This project is in Bangalore. This is a So this is a real picture. This is completed building in Bangalore in full precast wall slab system. I'll just show the photographs without going into the connection details of it. This is during construction, almost like the first few elements erected, and then this is the flooring, the topping, all the conduiting done in the flooring itself here. So you can see here each room size slabs are here. So these lines are the walls. So you have a room size slabs, mesh, staircase, everything is precast in this, including the pergolas and all, everything, this pergola features, everything is precast. This is the final look of the building, and no plaster, just paint over the precast panels. These are the interiors during construction. So as you can see, once the precast wall comes, all the electrical conduiting, junction box, everything is placed inside itself, provisions for plumbing, and after the panels are erected, the room is ready to finish. So just the paint and the flooring and the room is ready. So these are the interior looks of the precast. There is no plaster in this, just paint, maybe a little bit of putty. These are the references for the presentation. Thank you all for your valuable time. Thank you very much.
Thank you, sir, for your illustrious presentation. Now I request Mr. Anil Sheth, immediate past president, IS Truckee, Ahmedabad,